4 times in the past 2 years, physicists working with mammoth gravitational wave detectors have sensed something go bump in the night, sending invisible ripples through spacetime. Today, they announced the detection of a 5th such disturbance, but this time astronomers saw it too, at every wavelength of light from gamma radiation to radio waves. Just as physicists had predicted, the unprecedented view of the cosmic cataclysm, in which 2 superdense neutron stars spiraled into each other, brought with it a cornucopia of insights, each of which by itself would count as a major scientific advance. "It's really a big gift that nature has given us," says Alessandra Corsi, a radio astronomer at Texas Tech University in Lubbock. "It's a life-changing event." At 12:41 Universal Time on 17 August, physicists with 3 massive instruments, the twin 8-kilometer-long detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, in Hanford, Washington, and Livingston, Louisiana, and the 6-kilometer Virgo detector near Pisa, Italy, spotted waves unlike any seen before. The 4 previous events lasted for, at most, a few seconds, with gravitational waves rippling at frequencies of tens of cycles per second. The new sirens sang for 100 seconds at frequencies climbing to thousands of cycles per second. Whereas the earlier signal came from pairs of huge black holes quickly spiraling into each other, the new signal revealed lighter neutron stars, 1.1 and 1.6 times as massive as the Sun, twirling inexorably together, researchers announced in parallel press conferences in Washington, D.C. and Garching, Germany. The gravitational waves marked the beginning of a spectacular light show. Because black holes are the gravitational fields left behind when very massive stars collapse to infinitesimal points, they contain no matter that might radiate light when an isolated pair of them merges. In contrast, neutron stars are the dead cores left behind when slightly smaller stars explode in supernovae, and they consist of the nearly pure neutrons in the densest matter there is. When such orbs collide, they should spew debris glowing with light of all wavelengths. That's exactly what happened. 2 seconds after the gravitational signal, which only the automated trigger of the Hanford detector initially noticed, NASA's orbiting Fermi Gamma Ray Space Telescope picked up a blast of high-energy photons called a gamma ray burst. Within minutes, researchers at the Livingston and Virgo detectors confirmed the gravitational signal in their data. Still, it took LIGO the better part of an hour to issue a detailed alert, says Julie McHenry, an astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and a member of the Fermi team. McHenry says she found out about the gravitational signal as a coy rumor from a colleague who works on both Fermi and LIGO. A half hour after the Fermi alert, we got an email that said, "This gamma ray burst has an interesting friend," she says. Because all 3 gravitational wave detectors saw the signal, physicists could triangulate and locate the source to within a 30-square-degree patch of sky, about 60 times the size of the Moon, and much more precise than Fermi's localization. Astronomers swiveled telescopes large and small to the spot in the constellation Hydra. The search got off to a slow start because that part of sky was in daylight for many observatories. But within hours, 5 groups had identified a new source of light in the periphery of galaxy NGC 4993, which they watched fade from bright blue to dim red in a matter of days. Nearly 2 weeks later, the source began to emit X-rays and radio waves. In the end, more than 70 observatories studied the event. "This is first time we have a 3D IMAX view of an astronomical event," says Laura Catanati, a physicist at the Georgia Institute of Technology in Atlanta and deputy spokesperson for the LIGO collaboration. The combination of gravitational waves and electromagnetic observations scored at least 3 significant advances. First, it explains the origins of some gamma-ray bursts, the second most powerful known events in the cosmos other than merging black holes. Since the 1990s, theorists have thought that bursts shorter than 2 seconds originate when neutron stars merge to create a black hole. Longer bursts, lasting minutes, are thought to spring from the collapse of individual massive stars. The new result clinches the explanation for short bursts, says Peter Messeros, a theorist at Pennsylvania State University and State College. "It's tremendous," he says. "If you have gravitational waves with a burst, you know it has to come from a double neutron star." Second, the event reveals a hypothesized object called a kilonova because it briefly shines thousands of times brighter than an ordinary nova. As 2 neutron stars twirl together and rip each other apart, they should expel neutron-rich atomic nuclei, forming a shroud of matter totaling a few percent of a solar mass. Those nuclei beef up by gobbling neutrons in rapid succession and then quickly change their chemical identities through radioactive decay. That so-called R process, or rapid neutron capture process, should make the shroud glow for a few days, and its light should be reddened by heavy elements that soak up blue wavelengths. That's just what astronomers saw, says Brian Metzger, a theorist at Columbia University. "It's stunning. All of a sudden the curtain lifts, and what we see looks pretty close to what we expected." The observation of a kilonova scores a third advance by solving a long-standing puzzle in nuclear physicists, the origin of half the elements heavier than iron, including silver, gold, and platinum. Nuclear physicists have long thought that those elements are generated in our process, but haven't known where in the cosmos that happens, whether in the collapse of single stars or in merging neutron stars. The new find shows that some, and quite possibly all, of the mystery elements come from neutron star death spirals. "For me, as a nuclear physicist, this is an extremely important result," says Witold Nazarewicz, a theorist at Michigan State University in East Lansing, where experimenters are building a $730 million accelerator, in part to study the R process. The neutron-star merger presents some puzzles of its own. For example, the gamma rays were relatively faint, even though the burst was closer than any previously measured short burst by a factor of 10, McHenry notes. That could be because researchers saw the merger from a funny angle, she says. A gamma-ray burst is thought to emerge when jets of hot matter moving at near light speed shoot out along the rotational axis of the newborn black hole, beaming radiation into space like a lighthouse. In this case, observers on Earth may not be looking right down the jet but may be viewing it from a slight angle, McHenry says, astronomers' first off-axis view of an astrophysical jet. The long lag before astronomers began to pick up radio and X-ray emissions supports that picture, says Raffaella Margutti, an astrophysicist at Northwestern University in Evanston, Illinois, who studied the event with NASA's orbiting Chandra X-ray Observatory. The radio and X-ray signals come from the jet, which at first would have beamed them too narrowly along its axis to be seen from Earth. As the jet slowed, however, radiation would emerge at wider angles, making the signals detectable off-axis. Ever since LIGO announced the first gravitational wave event in early 2016, networks of small telescopes around the world have been poised to detect an optical counterpart. The race touched off by this latest event was won by Ryan Foley of the University of California, UC, Santa Cruz, and colleagues. They use 1-meter telescopes on Mount Hamilton in California and on Cerro Las Campanas in Chile to follow up LIGO Virgo alerts. At 23:33 Universal Time, 10 hours and 52 minutes after the gravitational waves arrived, the team used the telescope in Chile to snap an image of NGC 4993, and Charles Kilpatrick, a postdoc at UC Santa Cruz, saw a bright spot not visible in archival images of the galaxy. "Found something," he remarked coolly in an online messaging exchange. Within the 40 minutes, 4 other teams had independently discovered the same optical object. Rumors spread almost instantly over the internet. Within days, other scientists and journalists knew the outlines of the discovery, and the LIGO and Virgo teams struggled to keep a lid on the news until today's press event. That was no easy task, given the fact that astronomers tend to work in small, highly competitive teams, says Andrew Howell, an astronomer at UC Santa Barbara and staff scientist with the Las Cumbres Observatory, which also tracked the event. Used to working as a huge team, LIGO physicists were absolutely unprepared for the chaos that is the astronomical community, he says. Nonetheless, astronomers and astrophysicists came together to write a single compendious paper about the event. It has been submitted to, and some researchers say it has 4,600 authors, roughly 1/3 of all astronomers. In addition, individual groups are publishing dozens of other papers in and other journals, many concurrently with the announcement. With one spectacular event in the bag, the era of gravitational wave astronomy has begun. The next step is simply to see more such events and begin to do statistical analyses on them, astronomers say. But for the moment, the entire community is basking in the glow of the discovery and the stunning success of its models. "Sometimes I wonder whether we're all just mucking around," Howell says. "It's moments like this that reassure me that science works." Thanks for your watching. Please share this video and don't forget to subscribe.